Hello, welcome to Math for General Chemistry. Today we're going to be going over significant figures. We're going to be talking about what are significant figures, how we round with significant figures, and how we do calculations involving significant figures. So what are significant figures? Well, significant figures are the digits in a determination or a measurement, and how many digits there are shows the accuracy of those measurements. Now, this includes all digits, including the last digit, which is typically the most uncertain. Now, when we talk about measurements, sometimes we count, right? So for instance, on the screen there are 3 stars. I know with absolute certainty that there are 3 stars. So we could say that this is 3.0000000 stars. This is different than, let's say, if I have a measurement and I were to measure out 300 milliliters. Well, I know that there are 300 milliliters, but I don't know if it's 300.0000 milliliters. We also have infinite significance when we talk about conversions. So for instance, 1 inch equals 2.54 centimeters. This might as well be 1.00000, etc. inches equals 2.54000 centimeters. The fact that they're infinite significance means when we do calculations, these oftentimes don't determine how many significant figures are in the answer. But typically, we're not dealing with exact numbers, right? Counting. Typically in the lab, we're going to use measurements. So for instance, let's say we put a beaker onto a balance and we get 89.512 grams. That tells us how much accuracy the instrument has. Now, if you do this, sometimes when you use a balance, you'll notice that that last digit changes around. So it might be 89.512, then a few seconds later, 89.513, 511. That last one is the most uncertain. Now, the more digits we have in the measurements means that we can say it's a more accurate measurement. So for instance, let's say instead we used a different balance, the one we have on the right, and here we only have 89.5 grams, right? The one on the left that has more digits has more accuracy, right? It's telling us with more significance what that measurement is. Now, a key thing when we have a measurement in the lab, the more digits we have, the more accuracy typically means it's a higher end instrument, which costs more money. So let's look at some numbers that could be measurements and tell, based on that, how many digits there are, how much accuracy there is. So we have some rules for determining how many significant figures there are. So first, if it's a non-zero, so that's 1 through 9, those numbers are always significant. So for instance, 34.8, we have a 3, a 4, and an 8. All of those are non-zero, so we have 3 significant figures. 1352, we have 1, 2, 3, 4 significant figures. It becomes trickier once we have zeros in a number. So if we have zeros, it all depends on what type of zero it is. So we can call these zeros either captive, leading, or trailing. Captive zeros is when it's a zero in between 2 non-zero digits. So for instance, in this number down here, this 0 right here is a captive 0. It's between an 8 and a 2, right? 2 non-zeros. We also have what are called leading zeros. Leading zeros, like these 3 right here, these are in front of any non-zeros, right? If there was a 1 here, they wouldn't be leading, but seeing that there is none, these are leading. Leading zeros are never significant. I forgot to mention captive are always significant. The final one are trailing zeros. Trailing zeros are any zeros after all of the non-zero digits. Okay, so if this were a 5 here, this number, right, this 0 here would not be trailing, but without that 5, it's a trailing 0. It's after all of the non-zero. Now, trailing are a little more difficult, right? Trailing are significant if there's a decimal place in the number. So for instance, there's this decimal point right here. What that means is that it is significant here. If there weren't a decimal place here, it would not be significant. So let's go ahead and look at some examples. So let's say we have these 5 numbers, okay, 21.8, 21.08, 0.02108, and 0.021080, and 21,080. All of these have the same non-zeros, 2, 1, and 8. All of these are significant because they're non-zero. So seeing that this first number only has non-zeros, that means there are 3 significant figures. The next one, well, the 2, the 1, and the 8 are significant, so that's 3. But this 0, notice this is a captive 0. It's between 2 non-zeros. So that means it is also significant. Right? Captive zeros are always significant. So that means we have 4 significant figures here. Now, the same thing goes for this 0 here, this 0 here, and this 0 here. Right? Notice all of these, in the 3rd through the 5th numbers here, all have captive zeros between the 1 and the 8. So all those are significant. These ones here, the 0.0 in front of the 2, these are leading zeros. Leading zeros are never significant. So in this number right here, the 2, the 1, the 0, and 8 are significant, but these 0.0 are not. So this has 4 significant figures. Let's go on to this next one, 0.021080. Here, these, again, are leading, so that means they are not significant. This 0 at the end, this is a trailing 0. It is behind all of the non-zeros. Now, notice that this trailing 0, right at the end, we see it trailing in both of these last 2 numbers. Well, whether that 0 is significant all depends on whether there's a decimal place in the in there. Notice there's that decimal point. So what that means is that this 0 here is significant. So there are 5 significant figures here. This number does not have a decimal point. So that means this last 0, the trailing 0, is not significant, and therefore there are only 4 significant figures. So those are the rules for significant figures. Non-zeros are always significant. Captive, always significant. Leading, that means in front of all the other non-zeros, never significant. And then trailing zeros are significant depending on if there's a decimal point in there. Now let's go on to rounding significant figures. So rounding significant figures is something we often do when we have calculations. So let's say we do a calculation and we get on our calculator 45.0375, and I know I need to round this to 3 significant figures. All right, now first, let's look at this, 45.0375. Well, the 4, the 5, and the 375 are all significant because they're non-zero. And this 0 here, this is between a 5 and a 3, so it is a captive 0, so it's also significant. So this number has 6 significant figures. Well, we want to take this and we want to make it only 3 significant figures. So we first keep the 4 and the 5, right? The 4 and the 5 are definitely kept, right? So we go from left to right, we keep the 4, 5. Now the 0, we're also going to keep. But we may have to round it based on the next figure, which is the 3. In this case, the 3 is less than 5. And so if this digit, the one we're going to drop, is 0 to 4, we round down. So in this case, we'll round down, so this becomes 45.0. If it were 5 to 9, that first number we drop, that means we round up. Now, a better rule that you may learn in later classes is if it is a 5, you actually either round up or round down, and you do this to get towards an even number. But for this class, we'll just say 5 to 9, we round up. So let's look at 4 examples. So let's say we have 21.32, 43.78, 15.55, and 15.65. All right, and we want to round all these to 3 significant figures. Okay. Well, they all have 4 sig figs, so we need to get rid of this last one. So 21.32, I'm going to keep the 21 and maybe the 3, but I look at this 2. This 2 is less than 5, so I round down, and this becomes 21.3. I see this 43.78. I have 43.78 here. This 8 is above 5, so I'm going to round up. So this becomes 43.8. Here, 15.55. I round up to 15.6. And 15.65, I round to 15.7. Now, this last one actually, if you are going by those rules that you may learn in different classes, you would actually round down because you would round to even. But for this class, it's okay just to round up. We'll look more at rounding numbers for significant figures once we go on to calculations. All right, so we've talked about significant figures and when they are significant or not. We talked about rounding significant figures. Now let's go on to calculations. Now, you may have heard of the phrase, a chain is only as strong as its weakest link. What that means is if you had like a chain holding a dog or something, and it was really strong, except you have this one weak link right here, well, that weak link is going to break and the dog's going to escape, right? Well, the same is true for calculations. In calculations, the significant figures of your answer is dependent on the least accurate of all the numbers that go into that calculation, right? So if you have a bunch of measurements that you're going to use for your final answer, and all of those, a lot of those have, a lot of significant figures, right? A lot of accuracy, but one, you don't have a lot of significant figures, right? That one number is going to determine the accuracy of your final answer. All right, now how we do this depends on whether we're talking about addition or subtraction or multiplication and division. Let's look at addition subtraction first. In addition and subtraction, the number of significant figures is dependent on the number of decimal places in the values you're putting together. All right, so let's say we had 52.368 liters, and we're adding 4.1 liters. Well, I could do this on my calculator, and I would get 56.468 liters. Well, what I do is I look at these two values, and this one, 52.368, has 3 decimal places, right, to the right of that decimal point. This one only has 1. So here I have them lined up, right? So 52.368 and 4.1 liters. This line right here tells me, hey, I'm going to go by the one with the least amount. So I want to keep the 56.4, but I round this 4 based on the 6, right? The 6 is greater than 5, so it becomes 56.5 liters. This one measurement, which is the least accurate of them, is the one that determines how many significant figures are in my answer. Let's do another one. Let's say I have 53,500 milligrams and I'm subtracting off 1,256 milligrams. All right, so I have 53,500 and I'm going to subtract off 1,256. I put these into my calculator and I'm going to get 5,200 and 220 and 44 milligrams. Well, in this case, I look at it and I might think I'm done, but I'm not. Okay. What I have to do is I have to look at these two numbers. Okay? This one on the left, 53,500. Notice that these zeros here are not significant. Why? Because there's no decimal point, right? So this is the significance for that 53,500. Now, the 12,056 has those extra digits, but it doesn't matter. I need to round this number such that I only have significance up to this 100, the 100 place. So I might just say, well, if only the 522, I may just make this 522. But notice, there's a huge difference between 52,244 milligrams and 522, right? So what I have to do here is, even though I'm gonna just get rid of these bottom two, the 4 and the 4, I need to put zeros in there to save the space for those, right? That basically means that, hey, you know what? Even though we don't have significance in these digits, we know how big this value is. So this would be 52,200. And because this is a 4, we round down, and so that's why this is a 2. If this was 52,264, then we'd round it up. Right, so that's how we do calculations when we're dealing with addition and subtraction. Now let's look at multiplication and division. In multiplication and division, it's actually easier. In multiplication and division, we look instead at the number of significant figures in all the values that we use. So let's say we had 1.23946 centimeters, and we want to multiply that by 0.95328 centimeters, and multiply by 4.0 centimeters. This would be a measurement like if we were making finding the volume of a rectangular cube. Okay, so in this case, we do put it in our calculator, and we get 4.726209715 centimeters cubed. Well, that's what our calculator says. But what we have to do for our final answer is we have to look at the numbers involved. So this 1.23946 has 6 sig figs. 0.95328 has 5. This leading 0 is not significant. And 4.0 has 2. In this case, the 0 is significant. Why? Because it's a trailing 0 and there's a decimal point. So I have 6, 5, and 2. So I want my answer only to have 2 significant figures. So I look at this and I have 4.726. And I say I'm keeping the 4, I'm keeping the 7. And because this is a 2, I'm going to round down. This becomes 4.7 centimeters cubed. Let's try one with division. Let's say we have 9.308 grams divided by 1.27 centimeters cubed. Well, I put it in my calculator. I get this 7.329133858 grams per centimeter cubed, right? I take grams, divide by centimeters cubed, and that's how I get these units. Well, 9.308 has 4 significant figures. 1.27 has 3. So therefore, my answer should only have 3. So I'm going to keep the 7, keep the 3, keep this 2. But notice the next one is a 9, so I round up. So I get 7.33 grams per centimeter cubed. All right, so that is how we do calculations with significant figures. So in this video, we talked about what significant figures are, right? They're the measured digits in the determination that tells the accuracy. So the more significant figures, the more accurate. Now, we can tell the number of significant figures based on these rules. Non-zeros are always significant. Zeros are significant based on where they are in the number. If they're captive, right, such as 2, 0, 5, they're always significant. If they're leading, such as 0.205, this 0 is not significant. And if they're trailing, like 2.50, if they have a decimal point, they're significant. But if there's not, this 0 here is not significant. Now, when we deal with rounding of significant figures, we use the rule that 0 to 4 we round down, 5 to 9 we round up. And then finally, when we do calculations, addition and subtraction, we look at the number of decimal points, decimal places, while in multiplication and division, the number of significant figures. And the significant figures of our answer is dependent on the least accurate of the numbers involved.